Welcome to the Nocturnal Astronomer, your companion for drifting through the cosmos as you ease into sleep or simply let your mind wander among the stars. I'm your host, Atlas Reid, and tonight we're embarking on a gentle journey to one of the solar system's most enigmatic worlds. Uranus, that distant ice giant, awaits us with its peculiar tilt, its pale blue mysteries, and its quiet procession around the sun. We'll explore how this world was found, why it rolls on its side through space, what makes up its atmosphere and interior, and what secrets its many moons might hold. If you enjoy these types of videos, I'd be grateful if you'd give this one a thumbs up and consider subscribing to join us on future journeys through the night sky. And I'm curious, where are you watching from tonight, and what time is it where you are? Wherever you are, you're welcome here. Let's dive in. Imagine the night sky as astronomers knew it for thousands of years. 5 wandering stars, the planets visible to the naked eye, moved against the fixed background of constellations. Mercury, Venus, Mars, Jupiter, and Saturn were the known boundaries of our solar system. Then, on a clear March evening in 1781, a musician and amateur astronomer named William Herschel was surveying the sky from his garden in England. Using a telescope he'd built himself, a reflector with mirrors he'd carefully ground and polished, Herschel noticed something unusual in the constellation Gemini. At first, he thought it might be a comet. The object appeared as a small disk rather than a point of light, which was odd for a star. Herschel noted its position and returned to it on subsequent nights. The object moved, but not in the way comets typically moved. Its path was too slow, too circular. Other astronomers across Europe turned their instruments toward this curiosity. Calculations of its orbit revealed something extraordinary. This was no comet. Herschel had discovered a new planet, the first planet found in recorded history that hadn't been known to ancient civilizations. The discovery doubled the known size of the solar system in an instant. Saturn had marked the outer boundary at roughly 930 million miles from the Sun. This new world orbited at approximately 1,784 million miles out, nearly twice as far. The finding was so significant that it made Herschel famous across Europe. King George III of England granted him a royal pension, allowing him to pursue astronomy full-time. The question of what to name this new planet sparked debate. Herschel, hoping to honor his patron, suggested Georgium Sidus, or George's star. Others proposed Herschel itself. But ultimately, tradition won out. Just as Jupiter was named for the king of the Roman gods and Saturn for Jupiter's father, this new planet would be named for Saturn's father in mythology. Uranus, the ancient Greek deity of the sky, gave his name to this distant, mysterious world. From Earth, even through powerful telescopes, Uranus appears as little more than a pale greenish-blue dot. It's just barely visible to the naked eye under perfect conditions, at the very limit of human vision, which is why it was overlooked for so long. Its apparent magnitude, the measure of its brightness as seen from Earth, hovers around 5.7. For comparison, the faintest stars most people can see under dark skies are around magnitude 6. Uranus sits right at that threshold, appearing as faint as the dimmest stars, easily lost in the vastness of the night. Among all the planets in our solar system, Uranus holds a distinction that makes it truly unique. While most planets spin like tops, with their poles pointing roughly up and down relative to the plane of their orbit, Uranus rolls through space like a ball. Its axis of rotation is tilted 98 degrees from the perpendicular. Imagine taking Earth and tipping it onto its side so that the North Pole pointed almost directly at the Sun. That's essentially what happened to Uranus. This extreme tilt means that Uranus experiences the most unusual seasons in the solar system. Picture this. For 21 Earth years, roughly a quarter of a Uranian year, one pole faces the sun in constant daylight while the other pole sits in complete darkness. Then, as Uranus continues its slow 84-year orbit around the sun appears to rise over the equator. For the next 21 years, the equatorial regions receive the most sunlight. Then the opposite pole tilts toward the sun for another 21 years of continuous daylight while the first pole freezes in endless night. Think of it like a lighthouse lying on its side. As it rotates, its beam sweeps around the horizon rather than up into the sky. If you were standing on Uranus, depending on where you were and what season it was, you might experience 42 years of daylight followed by 42 years of darkness. The equatorial regions fare better, experiencing something closer to a normal day-night cycle, though even these regions endure wild seasonal variations. What could cause a planet to tip over like this? The most widely accepted explanation involves a collision early in the solar system's history. About 4 billion years ago, when the planets were still young and space was crowded with debris, something massive likely struck Uranus. This impactor would have been enormous, perhaps 1 to 3 times the mass of Earth. The collision didn't destroy Uranus but transferred enough energy and momentum to knock the planet onto its side. Think of it like hitting a spinning top with a baseball bat. The top doesn't stop spinning, but it might start wobbling or tilting at a crazy angle. Computer simulations suggest that such an impact could have occurred during the final stages of planet formation, when large bodies were still careening through the solar system, occasionally slamming into one another in catastrophic encounters. Some scientists propose an alternative scenario. Perhaps it wasn't one massive collision but several smaller impacts over time. Like a boxer taking multiple hits, each blow could have tilted Uranus a bit more until it eventually rolled onto its side. Another hypothesis suggests that gravitational interactions with other giant planets during the solar system's youth might have contributed to the tilt, though this alone probably couldn't account for such an extreme angle. Whatever the cause, this sideways orientation has profound effects on the planet. The unusual heating pattern, with poles receiving more sustained sunlight than the equator over time, creates strange atmospheric dynamics. You might expect the pole pointing at the sun to be much hotter than the rest of the planet, but measurements show that the equator and the sunlit pole have similar temperatures. Somehow, heat is being redistributed around the planet, though scientists are still working to understand exactly how this happens. The tilt also affects Uranus's magnetic field in peculiar ways. While Earth's magnetic field is roughly aligned with its rotation axis, Uranus's magnetic field is tilted 59 degrees from its rotational axis and offset from the planet's center. As Uranus rotates, its magnetic field wobbles like a misaligned spinning magnet. This creates a chaotic, corkscrew-shaped magnetosphere unlike anything else in the solar system. Charged particles from the sun spiral into this twisted magnetic environment, creating auroras that appear in unexpected places, sometimes near the equator rather than near the poles as they do on Earth. Uranus belongs to a category called ice giants, a term that distinguishes it from the larger gas giants Jupiter and Saturn. But don't let the name fool you. The ice and ice giant doesn't mean frozen water as you'd find in your freezer. Instead, astronomers use ice to describe materials that were in solid form in the cold outer regions where these planets formed. These include water, methane, and ammonia, substances that exist in various states throughout Uranus's interior. Imagine peeling back the layers of this distant world like an onion. At the very top, we encounter the atmosphere, the only part of Uranus we can directly observe from Earth and visiting spacecraft. This atmosphere extends down about 6,000 miles and consists primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. Hydrogen makes up roughly 83% of the atmosphere, while helium accounts for about 15%. But it's the remaining 2% that gives Uranus its distinctive color. Methane, that simple molecule made of one carbon atom bonded to 4 hydrogen atoms, pervades the upper atmosphere. Methane has a peculiar property. It absorbs red light but reflects blue and green light. When sunlight streams through Uranus's atmosphere, the methane filters out the warmer colors, leaving only the cool blue-green hues to bounce back into space. This is why Uranus appears as a serene, cyan sphere when viewed through telescopes. Descending deeper into Uranus, we pass through the atmosphere into what scientists call the mantle, though it's unlike any mantle you'd find on a rocky planet. This region, extending perhaps 12,000 miles down toward the core, is where things get truly strange. Here, water, methane, and ammonia exist under such extreme pressures and temperatures that they form what's known as a supercritical fluid, a state of matter that's neither quite liquid nor quite gas. Think of it like this. Normally, water can be ice, liquid, or steam depending on temperature and pressure. But if you squeeze water hard enough and heat it enough, it reaches a point where the distinction between liquid and gas disappears. It becomes a supercritical fluid, flowing like a liquid but expanding to fill space like a gas. In Uranus's mantle, these materials exist in this bizarre state, sloshing and swirling in the planet's interior. The pressures in this region are crushing. At the top of the mantle, pressures might be a few 100,000 times Earth's atmospheric pressure. Deeper down, near the core, pressures could reach 6 million times Earth's surface pressure. To give you a sense of scale, that's like having the weight of 250 fully loaded semi-trucks pressing down on every square inch of surface. No submarine, no deep-sea vessel humanity has ever built could withstand even a tiny fraction of such pressure. Temperatures in the mantle likely range from around 3,000 to 9,000 degrees Fahrenheit. Hot enough to melt rock on Earth, yet here these materials remain in their supercritical state because of the immense pressure holding them together. This hot, electrically conductive fluid might be responsible for generating Uranus's unusual magnetic field. Convection currents in this layer, combined with the planet's rotation, could drive the dynamo that produces the magnetism, though the details remain uncertain. At the very center of Uranus, there may be a small rocky core, perhaps half the mass of Earth. This core would be composed of silicate rock and iron, the heavy elements that sank to the center during the planet's formation. However, the line between the core and the mantle above it probably isn't sharp. Instead, there is likely a gradual transition zone where rock and the supercritical fluids mix. When Voyager 2 flew past Uranus in 1986, scientists were surprised by what they didn't see. The spacecraft's cameras revealed a nearly featureless pale blue sphere. Unlike Jupiter with its dramatic swirling storms and colorful bands, or even Neptune with its great dark spot, Uranus appeared calm, almost boring. Only a handful of clouds were visible, faint wisps against the uniform blue-green atmosphere. This apparent tranquility led some to conclude that Uranus was a quiet, inactive world. But appearances can be deceiving. The Voyager encounter happened to occur during Uranian spring, when one pole was pointing almost directly at the Sun. This unusual geometry might have suppressed atmospheric activity. As seasons changed and better telescopes came online, astronomers began to see that Uranus was far more dynamic than first thought. The atmosphere of Uranus is divided into layers, much like Earth's atmosphere has its troposphere, stratosphere, and so on. The lowest layer, The troposphere is where weather happens. This region extends from the top of the cloud layer down to where temperatures and pressures increase enough that we transition into the mantle below. In the troposphere, temperatures vary from around -370 degrees Fahrenheit at the top to slightly warmer temperatures deeper down. Clouds form in the troposphere at different altitudes depending on which compounds are condensing. The deepest clouds, made of water ice mixed with ammonia, form at the highest pressures. Above these lie clouds of ammonium hydrosulfide. Higher still, methane condenses into icy crystals, forming the bright white clouds occasionally visible from Earth. These methane clouds appear as bright spots against the deeper blue atmosphere because they reflect sunlight before it can be absorbed. Winds on Uranus are surprisingly fast. At the equator, atmospheric measurements show winds blowing up to 560 miles per hour. That's faster than the most powerful hurricanes on Earth and comparable to wind speeds on Neptune. These winds blow in the same direction as the planet's rotation, though scientists aren't entirely sure what drives them. On gas giants, heat from the interior typically powers atmospheric circulation. But Uranus emits very little internal heat compared to the other giant planets, making its powerful winds something of a mystery. Think of a pot of water on a stove. Heat from the bottom creates convection currents that cause the water to circulate. The giant planets work similarly, with internal heat driving massive circulation patterns in their atmospheres. But Uranus's stove is barely on. The planet radiates only about 1.1 times more heat than it receives from the Sun, far less than Jupiter or Saturn. Why, then, does it have such energetic winds? One possibility involves the unusual seasonal heating pattern caused by that sideways tilt. As one pole bakes in decades of sunlight, energy accumulates in that hemisphere. When seasons change and that energy starts redistributing around the planet, it might drive atmospheric motion. Another factor could be the depth to which sunlight penetrates. Uranus's relatively clear atmosphere allows sunlight to reach deeper layers where it can be absorbed and converted to motion. Storms on Uranus come and go. In 2006, astronomers observed a dramatic increase in cloud activity as Uranus approached its equinox, the point in its orbit where the sun shines directly on the equator. Bright clouds appeared at various latitudes, and a dark spot resembling Neptune's Great Dark Spot briefly appeared in the northern hemisphere. These features suggest that Uranus's atmosphere is capable of producing dramatic weather systems, even if they're not always visible. Temperature is another puzzle. Despite receiving one pole's worth of continuous sunlight for decades at a time, measurements show that Uranus's equator and its poles have similar temperatures. The planet must have some mechanism for transporting heat from the sunlit regions to the dark ones. Atmospheric circulation probably plays a role, but the details remain unclear. Despite being only the seventh planet from the Sun, not the eighth like Neptune, Uranus holds the title of coldest planet in our solar system. Its cloud tops can plunge to a frigid -371 degrees Fahrenheit, colder than Neptune even though Neptune orbits the Sun about 1 billion miles farther out. This counterintuitive fact reveals something fundamental about how planets retain and radiate heat. All of the giant planets in our solar system formed hot. The process of assembly, with countless smaller bodies crashing together and releasing their gravitational energy as heat, left these worlds with scorching interiors. Over billions of years, this primordial heat has been slowly leaking out into space. Jupiter still radiates about 1.7 times more energy than it receives from the Sun. Saturn radiates about 1.8 times more. Even distant Neptune emits roughly 2.6 times the solar energy it absorbs. But Uranus is different. It radiates only slightly more heat than it receives from the Sun, barely more than a planet with no internal heat source at all. It's as if someone turned off the furnace inside Uranus, leaving it to cool in the depths of space. The question of why this happened haunts planetary scientists. One hypothesis returns us to that ancient collision that may have tipped Uranus onto its side. Perhaps the impact did more than just knock the planet over. Maybe it was violent enough to disrupt the planet's interior structure in ways that affected how heat moves through the planet. Think of insulation in a house. If you compress it or disrupt it, heat might not flow through it the same way. Similarly, if the impact jumbled Uranus's interior, it might have affected how efficiently heat can travel from the deep interior to the surface. Another possibility involves the distribution of materials inside Uranus. If heavier elements didn't fully settle into distinct layers during formation, the interior might have a more uniform composition than other giant planets. This could affect convection, the process by which hot material rises and cool material sinks, carrying heat from the interior to the surface. With less efficient convection, heat might be trapped in the deep interior, unable to escape. There's also the chance that Uranus did cool down more than its siblings during the early solar system. If it formed with less initial heat or lost heat more efficiently when it was young, it would have less stored thermal energy to radiate away today. Time acts as an insulator in a sense. The longer heat has to travel from the core to the surface of such a massive planet, the more it cools along the way. Whatever the reason, this lack of internal heat has profound effects. It makes Uranus's atmosphere more stable and less turbulent than it might otherwise be. Without strong heat rising from below to drive convection, the atmosphere doesn't churn as vigorously as those of Jupiter or Saturn. This might explain why Voyager 2 saw so few clouds and why the planet appeared so uniform. The cold also affects the chemistry of the atmosphere. At such low temperatures, many compounds that would be gases on warmer worlds condense into ices. Methane freezes out of the atmosphere at higher altitudes than it would on Neptune, affecting cloud formation and atmospheric structure. The extreme cold creates conditions found nowhere else in the solar system, a natural laboratory for studying matter at the edge of what's thermodynamically possible. For comparison, the coldest temperature ever recorded on Earth was negative 129 degrees Fahrenheit at Vostok Station in Antarctica. Uranus's cloud tops are more than 240 degrees colder than that. It's colder than the surface of Pluto during parts of that dwarf planet's orbit. It's so cold that if you could somehow stand in Uranus's upper atmosphere, many gases we think of as normal, nitrogen, oxygen, carbon dioxide, would be frozen solid. When we think of planetary rings, Saturn immediately comes to mind with its spectacular, bright bands visible even through small telescopes. But Saturn isn't alone. Jupiter, Uranus, and Neptune all possess ring systems of their own, though far subtler and more difficult to observe. Uranus's rings were discovered quite by accident, through an event that showcased the cleverness and persistence of astronomical research. In March of 1977, astronomers were preparing to observe Uranus pass in front of a distant star. These events, called occultations, provide valuable information about a planet's atmosphere. As the planet moves between Earth and the star's light passes through the planet's atmosphere before being blocked entirely. By carefully measuring how the starlight dims and changes color, scientists can deduce properties of the atmosphere it passed through, like temperature, pressure, and composition. Several teams of astronomers, including one aboard a special airplane called the Kuiper Airborne Observatory, pointed their instruments toward the predicted path of the occultation. They began their observations early, wanting to catch every moment as Uranus approached the star. About 35 minutes before Uranus itself was due to block the star, something unexpected happened. The starlight briefly dimmed, flickered, and then returned to normal. Then it happened again. And again. 5 separate dips in the star's brightness occurred, each lasting just a few seconds. At first, scientists weren't sure what they were seeing. Some wondered if the measurements were errors or if perhaps Uranus had previously unknown moons. But as they continued watching, the same pattern of dips repeated after Uranus had passed the star, but in reverse order. The symmetry was striking and pointed to only one conclusion. Uranus had rings, and the starlight had been blocked as it passed behind these thin, dark bands of material. This discovery was revolutionary. Before 1977, Saturn was thought to be unique in possessing rings. Now Uranus joined that exclusive club, and soon after, rings would be found around Jupiter and Neptune as well. It turned out that rings might be common features of giant planets. Uranus has 13 known rings, each given names rather than numbers. The inner rings are named Alpha, Beta, Gamma, Delta, and Epsilon in order of their discovery and distance from the planet. Later observations revealed additional rings, including the broad, faint Mu and Nu rings, and eventually the extremely faint outer rings named Zeta, 6, 5, 4, and Gamma. The naming system is admittedly confusing, a consequence of discoveries spread over decades by different research teams. The rings of Uranus are nothing like Saturn's brilliant displays. They're dark, reflecting only about 2% of the sunlight that hits them. This makes them incredibly difficult to see. The material in these rings is thought to be mostly water ice mixed with some darker substance, possibly radiation-processed organic compounds or rocky material. Over time, radiation from the sun and cosmic rays bombards the ice, darkening it and turning the rings into the charcoal-colored bands we observe. Think of fresh snow compared to old city snow that's been driven through and polluted. Fresh snow is brilliant white, reflecting most light that hits it. Dirty, old snow is gray and dingy, absorbing more light than it reflects. Uranus's rings are like that old snow, darkened by eons of exposure to space. The rings are also remarkably narrow. The Epsilon ring, the brightest and most substantial of the system, varies in width from about 12 to 60 miles. For comparison, that's narrower than the distance across many cities. Saturn's main rings span thousands of miles in width. Yet despite being so narrow, the Epsilon ring extends all the way around Uranus in a nearly perfect circle. What keeps these rings so narrow? On their own, rings tend to spread out over time. Particles collide, some speed up and move to higher orbits, others slow down and move to lower orbits, and gradually the ring becomes broader and more diffuse. But Uranus's rings stay confined. The answer involves shepherd moons, small satellites that orbit just inside and outside the rings. Their gravity nudges wayward ring particles back into line, much like a shepherd dog keeps a flock of sheep together. 2 such moons, Cordelia and Ophelia, were discovered by Voyager 2 flanking the Epsilon ring. Their gravitational influence keeps the ring particles corralled. Similar dynamics probably shape the other rings, though not all shepherd moons have been found yet. Some may be too small to have been detected. Uranus doesn't journey alone through the outer solar system. It's accompanied by at least 27 known moons, a diverse family of worlds ranging from tiny captured asteroids to substantial spheres large enough to have their own geological histories. Unlike most moons in the solar system, which are named after figures from Greek and Roman mythology, Uranus's moons take their names from characters in the works of William Shakespeare and Alexander Pope. This literary tradition gives the Uranian system a distinctive character. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, were all discovered through telescopes from Earth between 1787 and 1851. William Herschel, who discovered Uranus itself, also discovered the first 2 moons, Titania and Oberon, in 1787. He spotted them as faint points of light near the planet, moving in ways that indicated they were bound to Uranus by gravity. Titania, the largest of Uranus's moons, measures about 980 miles in diameter, roughly half the size of our own moon. Its surface is a tapestry of craters, canyons, and ridges, suggesting a violent past. The Messina Casamata, a canyon system on Titania, stretches for nearly 1,000 miles, cutting deep into the moon's icy crust. This enormous crack hints at internal forces that pulled the moon apart, perhaps caused by the freezing and expansion of a subsurface ocean early in its history. Imagine water freezing in a bottle. As it turns to ice, it expands, and if the bottle is sealed, it might crack or even burst. Something similar might have happened to Titania. If it once had a liquid water ocean beneath its icy surface, the gradual freezing of that ocean would cause the interior to expand, fracturing the surface and creating the canyons we observe today. Oberon, the second largest and outermost of the major moons, also bears the scars of impacts and internal activity. Its surface is heavily cratered, testament to billions of years of collisions with debris. But some craters on Oberon have dark material on their floors, possibly a mixture of ice and carbon-rich compounds that erupted from the interior when impacts punched through the surface. This suggests that Oberon's interior was once more active, perhaps warmed by radioactive decay or tidal heating. Ariel presents perhaps the most geologically young surface of the major moons. Its terrain is crisscrossed with valleys, faults, and ridges, and it has fewer craters than Titania or Oberon, suggesting that geological activity has resurfaced parts of Ariel more recently. Valleys on Ariel appear to have been filled with some kind of material, possibly ice that flowed like a very slow liquid or slushy mixture that oozed across the surface. Scientists call this cryovolcanism, a type of volcanism where the lava is water, ammonia, or other substances that are liquid or slushy at the frigid temperatures of the outer solar system. Umbriel, in contrast, appears ancient and dark. Its surface is the darkest of the 5 major moons, reflecting only about 16% of the sunlight that strikes it. Umbriel is heavily cratered with few signs of recent geological activity. One feature stands out, a bright ring about 90 miles across called the Wonder Crater. This unusually bright feature on an otherwise dark moon remains something of a mystery. It might be a relatively recent impact that exposed fresher ice, or it could be deposits of bright material transported from elsewhere on the moon. And then there's Miranda, the smallest of the 5 major moons, but perhaps the most bizarre. When Voyager 2 captured detailed images of Miranda in 1986, scientists were stunned. The little moon, only about 290 miles in diameter, displayed a chaotic jumble of terrain unlike anything seen elsewhere. Enormous faults cut across its surface. Strange polygonal regions called coronae, areas of grooved and ridged terrain, sit alongside heavily cratered plains. One feature in particular captured attention, Verona Rupes, a cliff that drops nearly 3 miles down, the tallest known cliff in the solar system. To give you a sense of scale, that's about 15 times taller than the walls of the Grand Canyon. Due to Miranda's weak gravity, if you could somehow jump off Verona Rupes, you'd fall for about 12 minutes before hitting the ground, plenty of time to contemplate your decision. Miranda looks like it was taken apart and reassembled. One theory suggests that the moon was indeed shattered by a massive impact and then reformed from the pieces. The story of humanity's exploration of Uranus is brief but remarkable, centering on a single spacecraft that ventured farther from home than any mission before it. Voyager 2, launched in August of 1977, was part of an ambitious plan to visit the outer planets during a rare alignment that occurs only once every 176 years. This alignment allowed a spacecraft to use gravity assists, stealing a tiny bit of momentum from each planet it passed to slingshot onto the next destination. Voyager 2 first flew past Jupiter in July of 1979, then Saturn in August of 1981. Each encounter provided gravitational boosts that sent the spacecraft deeper into the solar system. By the time Voyager 2 approached Uranus in January of 1986, it had traveled for more than 8 years and covered over 1,700,000,000 miles. The spacecraft carried a suite of instruments including cameras, spectrometers, magnetometers, and radiation detectors. Engineers and scientists had designed these instruments in the 1970s, before modern computers and electronics. The entire spacecraft communicated with Earth using a transmitter powered by about 23 watts, less power than a typical refrigerator light bulb. Yet this faint signal had to travel nearly 2 hours at the speed of light to reach Earth. On January 24, 1986, Voyager 2 made its closest approach to Uranus, passing within 50,000 miles of the cloud tops. During its brief encounter, the spacecraft discovered 10 new moons, confirmed the existence of the ring system, measured the planet's magnetic field, and captured hundreds of images. But the encounter was challenging. Uranus was so distant and dim that exposure times for photographs had to be long, and the spacecraft had to be precisely positioned to avoid blurring. The images revealed a world of subtle beauty. The pale blue-green globe, nearly featureless in visible light, hinted at hidden complexity. The moons, especially Miranda, proved far more interesting than expected. The discovery of the tilted, offset magnetic field raised new questions about the planet's interior. And the detailed measurements of temperature, composition, and atmospheric structure provided data that scientists continue to analyze decades later. After Uranus, Voyager 2 continued to Neptune, its final planetary encounter, before heading out into interstellar space where it travels still, now more than 12 billion miles from home. No spacecraft has returned to Uranus since. The ice giant remains one of the least explored planets in our solar system, visited only once during a brief flyby. But that may change. In recent years, planetary scientists have advocated strongly for a dedicated mission to Uranus. In 2022, a major scientific review by the National Academies of Sciences recommended that NASA prioritize a Uranus orbiter and probe as its next large planetary mission. Such a mission could spend years studying the planet, watching how its atmosphere and magnetosphere change with seasons, examining the moons in detail, and perhaps even sending a probe plunging into the atmosphere to measure its composition directly. Questions abound that only a new mission could answer. What lies beneath those tranquil cloud tops? How does heat move through the planet's interior? Do any of the moons harbor subsurface oceans that might support some form of life? What caused the unusual magnetic field? How do the rings maintain their structure over billions of years? What is the detailed composition of the atmosphere, and are there complex organic molecules forming in those frigid clouds? Understanding Uranus also helps us understand planets beyond our solar system. Many planets discovered orbiting other stars are similar in size to Uranus and Neptune. These Neptune-mass planets appear to be common throughout the galaxy. By studying Uranus in detail, we gain insights into how such planets form, evolve, and behave. Each discovery at Uranus informs our understanding of thousands of worlds light years away. There's something humbling about Uranus. It reminds us how much we don't know, how many mysteries remain even in our own celestial neighborhood. Here is a world we've known about for more than 240 years, yet we've spent fewer than 6 hours examining it up close. It orbits in the dim outer reaches of our solar system, patient and enigmatic, waiting for humanity to return with better instruments and deeper questions. And on that note, we conclude our peaceful exploration of Uranus, that sideways giant rolling through the darkness. We've journeyed from its accidental discovery to its icy moons, from its peculiar magnetism to its shadowy rings, from the mysteries of its formation to the possibilities of future exploration. Thank you for joining me on this voyage through the outer solar system. I hope you found some wonder in these distant, frozen realms, and perhaps some peace in contemplating the vastness and strangeness of our cosmic home. Until next time, keep looking up.